first. So I'll draw it out, but understand that you guys already have this filled in on the next slide. I just feel like it's a little bit easier for you guys to follow as I'm drawing it out too, okay? But I'll use the same exact steps as what you guys have over here, okay? So essentially, everybody, steps 1 through 8 is gonna be on this slide. The rest of the steps are gonna be on this one here. And there's gonna be some modifications on here based on the ABP rules, okay? Would one of you guys mind flipping off my switch, please? Thank you, thank you. My handout. Okay, the very first step in excitation contraction coupling, and I want you guys to understand that excitation contraction coupling can also include part of a mechanism in chapter 7, which is neurotransmitter release, okay? Are you okay? Because you're like super red right now.
I always get red. We've been known for this.
Okay, I just wanted to make sure it wasn't because of
No, I'm
me.
good. I was sweating though.
Okay.
I was laughing so hard.
Sorry. Okay, so the very first step here is an action potential. Is going to travel down to your synaptic end bulb, your axon end bulb. Everybody here clear? That's the very first step. When the action potential reaches the axon terminal, so here's step 2 now, voltage gated calcium channels will open up. And when they open up, they'll allow a bunch of calcium to go inside your axon terminal. Everybody here clear? Calcium going in then will cause these vesicles containing acetylcholine to dock onto the membrane and release acetylcholine into, what's that space called? Synaptic cleft. Everybody here good? Still following? Okay. Okay. The next thing that has to happen then, which is step 4, is acetylcholine binds to its receptor. What are these receptors called? Nicotinic cholinergic receptors. And because nicotinic cholinergic receptors are ligand gated, what kind of ion channels? Sodium channels. When acetylcholine binds to them, right here, what is going to go inside the cell? And when you have a bunch of sodium going inside the cell, what is happening in terms of an electrical event on that motor end plate? It's a depolarization. So at this point, I will write a bunch of plus signs here to indicate that this is now depolarized. It is positive, it is now depolarized. Hey, that depolarization event has a special name if it's on that motor end plate. What is that called? End plate potential. So again, what's an end plate potential, everybody? What's an EPP? That's a depolarization where? That's a depolarization where? At the motor end plate, okay? So step 4 is when acetylcholine binds the nicotinic cholinergic receptor. Step 5 is where you have a bunch of sodium rushing inside the cell, causing that motor end plate to depolarize. And what do you now have? An end plate potential. Do depolarization events stay at the same place, or do they spread? They will always spread. So I want you guys now to notice At this point, that end plate potential doesn't stay there, so now we are at step 6, where you have the action potential travels down, what kind of tubules? T tubules. And let me explain why here, okay? You have this end plate potential. What kind of channels are your nicotinic cholinergic receptors? Ligand or voltage gated? They are ligand gated sodium channels. But hey, didn't I depolarize that, didn't I depolarize that motor end plate? Which means I changed the charge on it, right? There are other these now are what we would call voltage gated sodium channels. Okay, so when you have that end plate potential, it's gonna spread and it's gonna cause voltage gated sodium channels to open, and when those open, what else goes inside the cell? Sodium. So your action potential then travels down into the T tubules. Everybody here clear? Okay. Well, when you get down into the T tubules, okay, and I'm gonna call this step 7A and 7B, okay? When you go down into the T tubules, you will have these receptors called DHPs opening up. Okay, I'm gonna write it down at the bottom. So DHP stands for dihydropyridine receptors. These are voltage gated calcium channels on your T tubules. Okay. So the action potential travels down the T tubules, your DHP opens. But almost simultaneously, you're gonna notice that these DHPs are going to be physically tethered to another type of calcium channel that is on your sarcoplasmic reticulum. So here's the SR, right? So if that is a DHP, this guy right here is called an RYR. And RYR stands for a ryanodine receptor, also known as calcium release channels. Okay. So what happens here is that the action potential causes DHP to open, but DHP is physically tethered to RYR. So when DHP opens, it automatically also opens your RYRs. Everybody here clear? What's stored in your sarcoplasmic reticulum in that terminal cisterna? Calcium. So as soon as RYRs open,
This is all for the lecture exam, right?
this is all for your lecture and your lab practical. Told you guys that this is basically a page-long mechanism on your lab practical too, and you fill in the blanks for it, okay? So as soon as RYRs open, so step 8 then, is calcium is going to flood the sarcoplasm. From where? The sarcoplasmic reticulum. Everybody here good? Yes? Okay, so this is the first 8 steps. Mull it over right now. But remember, you do have this part right here, which basically kind of talks to you about the whole thing again. So I'm going to talk about it here. The only thing that's missing here is the voltage gated sodium channels, okay? So step 1, action potential travels down the axon, reaches the axon terminal. When it reaches the axon terminal, you will end up opening voltage gated calcium channels on that axon terminal. Calcium influxes into the axon terminal and causes vesicles containing acetylcholine to dock onto the membrane. Acetylcholine is released into the synaptic cleft. Acetylcholine then binds what kind of receptors? Nicotinic cholinergic receptors. And when it binds, the channel portion of those nicotinic cholinergic receptors opens, allowing what ion to go inside the motor end plate? Sodium. So there's a sodium influx, okay? Because there's a bunch of sodium coming into the motor end plate now. You depolarize that motor end plate. That is an event called an end plate potential. Everybody here clear? So you only call it an end plate potential if and only if it's where in the sarcolemma? Motor end plate. That end plate potential, because it is a depolarization event, opens voltage gated sodium channels elsewhere along the sarcolemma, causing sodium to come in. You then cause another depolarization event, which now becomes a full-blown action potential. That action potential then travels down into the T tubules. Everybody here clear? Because an action potential has a depolarization event associated with it. That depolarization event will open voltage-gated calcium channels on the T tubules called DHPs, or dihydropyridine receptors. Everybody here clear? But DHPs, as soon as they open, they're physically tethered to another type of calcium channel, a calcium release channel, on what organelle? The sarcoplasmic reticulum. So as soon as DHP opens, it also forces the ryanodine receptors to open on that SR. Everybody here clear? And when the ryanodine receptors open, calcium leaves the SR and floods the cytoplasm. Why is that important? Because what does calcium do? Calcium is our key. So now we're at this point here, okay? So normally, what blocks the myosin binding sites on actin? Tropomyosin. What keeps tropomyosin in place? Troponin, right? Everybody here clear? So as soon as calcium floods the cytoplasm, we are now at step 9 here. As soon as calcium floods the cytoplasm, calcium binds what protein? Troponin. Troponin undergoes a conformation change. It then moves what out of the way? Tropomyosin out of the way and exposes myosin binding sites on actin. So now we're at this part here. This portion is the actual sliding filament theory. And what you're gonna notice is that in your lecture sets, okay, I kind of go backwards. I start with sliding filament theory first, and then we move back and combine everything together. So hopefully, after having this lecture today, when you watch that, it's not gonna be so strange to you anymore, okay? So again, you expose the myosin binding sites on actin, what can you now form? Myosin cross bridges, okay? So I want you to look here. What do you have attached to that myosin head? ADP and, so what do I not like about this picture?
No, ADP.
What do I not like about this picture here? It's ADP in a phosphate group. What should that look like already? Attached or detached?
It should be attached.
Attached, because what does it have?
Well, phosphate.
ADP. It has ADP. So you guys now need to modify this picture for me. Because at this point, because ADP is now present, this myosin head is attached. You now have something called a cross bridge. When it attaches, which is now what you see here, I want you now to see that myosin head is now popped, meaning it is primed to undergo what kind of stroke? Power stroke. Everybody here clear? Notice how this is attached and that's attached, right? ADP is present. What do you need to get rid of to release energy? The phosphate group. So I want you to notice here how when the phosphate group is released, okay, energy is released and you move actin where? Towards the center, okay? This is now what we would call a power stroke. Phosphate is released. Energy is used to move. Energy is used to move what? Towards the center? Actin. Everybody here clear? Okay. You have ADP still, right? When ADP is still present, should your head be attached or detached? Still attached. What's wrong with this picture?
Detached.
What's wrong with this picture? What does myosin not have here? Doesn't have ADP, so for it to stay attached, ADP must still be around, okay? And for you to release it, what do you need? Okay, there you go. When ATP, so now I want you guys to look here, right? ATP is attached now. Notice how it's not physically connected anymore. Does everybody see it? Okay. I want to undergo another contraction cycle. What do I need to do now? Okay, but what is that enzymatic activity called?
The myosin ATPase.
Yep. And when you have ADP plus a phosphate group, what can you form again? A cross bridge. Notice how this thing is gonna keep going as long as two things are present. Calcium, because notice how calcium is your key and exposes that binding sites. And then what causes the release of calcium? Binding of what neurotransmitter? Guys, come on, not a trick question. We just went over this. Acetylcholine. Acetylcholine. Okay. So I want you guys to think about this in terms of steps. Acetylcholine binding induces the release of what from the SR? Calcium. Calcium being released causes troponin to move tropomyosin out of the way. And then what can you now form? Myosin cross bridges. And this cycle is going to keep happening so long as A, the myosin ATPase activity works, and B, calcium is still present. And what causes calcium to still be present? Acetylcholine binding. So you keep going through this process until you get rid of acetylcholine. Everybody here clear? Okay, so this is the excitation, contraction, coupling summary, so make sure you read that. I also go over this in your lecture videos, so pay attention to it. But here's what happens, okay? Do you remember a few slides back? Not a few slides, a lot of slides back. Sorry. Do you remember this picture right here? Remember I told you why you always have to have a space, that synaptic cleft? Because what's gonna be in that space? Acetylcholine esterase, which are the enzymes that regulate the activity of acetylcholine, because what they do is they break them down. So if you want to stop your muscle contraction, acetylcholinesterase needs to do what to acetylcholine? Breaks it down. If acetylcholinesterase is active, it's going to break down acetylcholine. And if you don't have acetylcholine, okay, I'm gonna ask you, hey, if you don't have acetylcholine, what do you not have on your motor end plate? You don't have an end plate potential. And if you don't have an end plate potential, what do you not have going down? You don't have an action potential going down the T-tubules. And if you don't have an action potential going down the T-tubules, do you open DHPs? No, you close them. And because DHPs are physically attached to RYRs, as soon as DHP closes,
So does DHP.
no, DHP is first. As soon as DHP closes, your RYRs also close. Does that make sense to everybody? Hey, and if your RYRs close, can calcium get out? No. So now you have another problem to solve. Okay, you closed all of the RYRs, but don't you have a bunch of calcium inside the cell already, in the cytoplasm? So what do you have to do? You need to get those calcium back into the sarcoplasmic reticulum, and you do that by using something called Circa pumps. Your sarcoplasmic reticulum, what kind of endoplasmic reticulum is that? Is that smooth or rough? It's smooth, hence Circa pumps. Smooth endoplasmic reticulum calcium pumps. They will literally take whatever calcium is in the sarcoplasm and pump it back into the SR. Everybody here good? At that point, you have no more calcium. And if you have no more calcium, troponins gonna move tropomyosin back. Everybody here clear? And if tropomyosin is moved back to where it was, what are you now blocking? Myosin binding sites. And if the myosin binding sites are blocked, what can't form? The myosin cross bridges. So at that point, if there are no more cross bridges, you're gonna assume what is attached to your myosin heads? ADP or ATP? ATP. Does that make sense to everybody here? Yes? Now do you guys understand why I was super slow today? Okay, so hopefully going through that makes it a little bit easier for chapter 12. I will see you guys tomorrow. I'm done for the day. Sweet! Yes! Does it all make sense?